So the daily problem is number of good paths. You can pause to read it. But the idea is we're given this graph representing a tree. So we know that it's a graph and it's a tree structure. So each node will have a certain number of child nodes and there's no cycles and stuff. And what we're looking for are good paths. So good paths are paths between two nodes of the same value. Each node has a value ascribed to it along with the node number. And we want to find paths between two nodes of the same value where they never traverse a node of a higher value. So for example, node 1 and node 4 both have a value of 3, and you can traverse them by traversing 1, 2, 3, or 3, 2, 1, or whatever. Whereas like node 0 and node 3 both have a value of 1, but there's a 2 in the way, so these are separate from each other. And some specifics, if we look here at this first one, this is the only path we can trace, but the answer is 6. That's because each node can trace a path to itself. So immediately we know the answer is always going to be at least the number of nodes in the tree. And this is a pretty complicated one. You can kind of think of a brute force solution fairly quickly, but as one would expect from a problem of this difficulty, it doesn't pass the time constraints. So I thought it would be interesting to go over like the solution, the fast solution, and then maybe at the end explore through my code, because it deviated. Last night I was kind of in a manic state, waiting for the coding competition that happens every Saturday, and I came up with a weird solution that definitely holds its own. It gets about 90th percentile, but it's not the standard solution for this. So the standard solution involves some graph theory, and I'm going to go over that quickly. If you haven't heard of Prim's algorithm or Kruskal's algorithm, they're not very scary. They're some of the more approachable graph algorithms. So we'll go over those. We'll go over union and find slightly, but yesterday's daily problem really covered union and find. So if you want an in-depth look at that, look at yesterday's video if you want. But yeah, we'll just jump into the logic. So first things first, n is the number of nodes. That's just going to be the length of values, or the length of edges plus 1 theoretically, but I think, yeah. So we have that, and surprise, surprise, we're going to use union find. So we're given this list of edges. Usually, in this situation, you just immediately turn it into an adjacency list. That's always my first instinct, and that was my first instinct. But here you don't actually have to do that. And this is where I'm going to talk about these different algorithms for a second. So buckle up, it's going to be related. But the basic idea is that if we sort the edges by the maximum, we'll say something like edges dot sort, and then key equals lambda x. So the key for sorting is if you said key equals lambda x, x plus 1, wouldn't change the order in any sort that does that, but that would mean like instead of using the number as the key to sort to see if it's greater or less, use the number plus 1. So we're going to say lambda x. So instead of using, if we're sorting edges, instead of using this list containing two integers that are the nodes, edges at I are going to be node A and node B designated as connected. Instead of using those as the basis for sorting, because that doesn't really mean much, we're going to say what we actually want is the maximum between vals at x at 0 and vals at x at 1. So, and then I'll just print edges and return 6, because this example the answer is 6. So the other ones for false, this is true just because I want to see the green. But if we print out edges, we can see we've sorted this in a specific way. Now 0 and 2 are the first two nodes to be connected, and then 2 and 3, and then 0 and 1, and so on. So the idea is when we've sorted it this way, whereas before edges was in this pattern, we had 0 and 1 first. Now 0 and 2 is first. And the reason why we're doing this is we can see, well, 0 and 1, the values of these nodes are 1 and 3. Whereas for 0 and 2, it's 1 and 2. And then 2 and 3, the values are 2 and 1. So we've sorted it so that we have the edges with the lowest values being connected first, being measured as the maximum between each of these two values. So at any given point, as we count up, the maximum between these two values will go up as in ascending order. So we can see 0 and 2, the maximum is 2. 2 and 3, the maximum is also 2. 0 and 1, the maximum is 3. 2 and 4, the maximum is 3, between the values of each of these nodes. So why are we doing this? This gets to Kruskal's algorithm. And first things first, both of these algorithms are creating minimum spanning trees. So minimum spanning tree, if we look at Kruskal's, finds a minimum spanning forest, very similar. And a minimum spanning tree is, if you think of a graph as each of these are locations, and every line that you draw is a road that has a certain cost in like a weighted graph, a minimum spanning tree is the cheapest possible way that you can connect all nodes. So we see here that every single node is selected. Every single node is part of this big tree. And for example, this 1 and this 3, that adds up to 4. So we could have said, okay, you connect to here. You connect to here, and it costs 4 if you do this way, but it also costs 4 if you do this way, and you get this node. As opposed to if you did something like spend 5 to go here, and then 1, and then 3. That would be 1 more cost than spending 4 to go here, and then 1, and then 3. So minimum spanning forests and minimum spanning trees have a lot of uses. Minimum spanning forests are just potentially not one connected component, but we're dealing with a minimum spanning tree. They have a lot of uses, and the use here is a little bit not obvious because we're already given a tree structure. So actually we have to iterate through every single edge and edges to have a tree that includes everything. If we didn't, then like we already have a tree, and if we didn't include every edge, then we're going to be missing. We're going to have 2 trees. And also, our thing isn't really weighted. We don't have any weights between these edges. We just have values at each node. So how the hell does this relate? Well, I'll go over how to find minimum spanning trees, and then hopefully bridge the gap from there to how it relates to this. So the first way, not the first way, one of the 2 ways to find a minimum spanning tree, I find this graph, this GIF really useful, is to start at any random node, connect the shortest length or the lowest weighted edge to that node, and then now you have 2 nodes, and amongst those 2, look at every node that's potentially adjacent and attach the lowest weighted edge. Here it's going by distance, so it's literally the tree that's going to have the shortest distance of red line. But you can kind of think of that as a weight, just very explicitly spatially shown. So it starts here and it says, this is closer than this. Oops. This is closer than this. So connect these 2. And then now you're looking at 2, and then we say, well, between this and every other point and this and every other point, these 2 are the closest. So connect those. And then between these 3, we say, well, now this is the closest to any of the nodes that we have. So connect those. And so on. And we can see it bridges this, and then it's going to be that, and then it's going to be that, and then this, and then this, and then these ones. Or I guess this node is closer to this than that was, but you get the idea. So what we're doing here is we have a collection of nodes that are in our tree currently, and then we're just looking for the shortest path we can draw to collect a new node. That's as opposed to Kruskal's, that's very similar, but what it's doing is saying just draw the shortest connection in general, as long as you're not connecting 2 nodes that are already connected. So we can see it showed that blue right there and said, hey, try this connection, that's the shortest, but it's not going to work because this is already a connected component. You're not adding anything, you're not combining any. So we'll see eventually it'll connect this because this will be the shortest distance that combines a new tree. And then eventually it'll probably connect this or this. Yeah, it connected that. We'll probably see this connect at some point very soon. We can see it's testing all the things between 2 nodes that are already in the same tree. And then eventually it'll connect one of these. And These both do effectively the same thing. They construct this minimum spanning tree. Prim's algorithm is better. I forget which way it is. I believe Prim's algorithm is better if you have a lot of nodes with not that many connections between each node. And this is a lot better if you have a lot of edges between not that many nodes. So that's a little bit of graph theory. It relates to this because that's very similar to what we can do if we sort the edges by the maximum value. What we can say is connect node 0 and connect node 2. These both have a value of 1. Or I'm sorry, they have a value of 1 and 2. I don't know why I said that. That's the smallest possible connection we can make if we think of these connections as bottlenecks, where, for example, this 3 is bottlenecked by this connection. And once this connection is drawn, this 3 can traverse it. But let's say this was like 4 and this was 5. Once this connection is drawn, that actually doesn't really affect this 3 at all, because this 3 can't traverse that anyway, so that connection might not as well exist. So the idea, and what we're eventually going to do, is iterate through each of these edges and to draw the connection, very similar to Kruskal's algorithm, draw these random connections that are as small as possible and see if they connect anything. So for example, let's say this was our tree. These were random nodes in our tree, these two things. And once we draw this connection here, we say, hey, are any of these nodes the same value? Because if so, then we can add to our ultimate answer that we're going to return. And then the idea is we have this big connection here, and any connection we draw after that is either going to have the same maximum value. For example, 0 and 2 is 1 and 2. 2 and 3 is 1 and 2 as well. So that has the potential to add new good paths, or it's going to be greater, in which case we don't really care about any of these lower numbers anymore because we've already checked them. And for example, let's say all of these nodes here had values of 0 to 3, but then this connection had let's say this node had a value of 4. All of these nodes will not be able to connect with anything past that because this 4 node is blocking them off. So when we draw this connection, we want to draw it after we've drawn all of these connections. And when we draw all of these connections, we can see, hey, there's a 1 here and a 1 there. Eventually they connect, and now we have a good path there. But let's say there's a 1 here. We want to draw this connection before we draw this connection, because then we can just say, hey, this is connected to some structure down here, whatever. Maybe there's 1s, maybe there's not, that form a good path. But we're considering this component not connected with this component when we're looking at 1s. Because if this value was 4 for this node, then that's going to block any 1s anyway. It's as if these nodes aren't connected when it comes to anything less than 4. And then eventually we draw this 4 connection, and then later on we say, hey, this component and this component are all part of the same component now. So if there's like an 18 here and an 18 there that wind up being connected, then we can see that they're connected because this, because this connection using a 4 or these connections using a 4 is less than 18. So it's a little bit long-winded. I don't know if I'm doing the best job of explaining it, but I think also starting to code sometimes helps illuminate the specifics of the logic. So we've sorted edges, and spoiler alert, we're going to use union and find. So I'll say root and size equals I for I in range n, and 1 times n. And for a quick refresher, this is the size of each connected component, and this is the root node that we're choosing as the marker node for each component. So when we start, it's just a bunch of we haven't drawn any of these edges. It's a bunch of isolated components of each node being itself. And then we'll say answer equals 0, and then in the end we're going to return answer. And let's define find of A and define union of A and B. And this is definitely going to be modified. because we're not we're taking into account the values of each node in the connectivity. So find of A is very straightforward. I'm just going to do what I always do. So we want to return the marker node that corresponds to A. So we'll say while root at A doesn't equal root. Okay, so that's find complete. And then for union, we're going to say A, B equals find of A and find of B. So now we're looking at the marker node. Let's say these three are connected and these two are connected, and this is the final edge that we're drawing. It's not, because this edge is actually the first that we're drawing. This or this would be the final edge that we draw. But let's say we have some connected component here and some connected component here, and we draw this line. What we want to look at is, does this line connect any nodes that form a good path? And because we've sorted by the maximum value of both nodes in this connection, that means that we know that the only good path this could possibly form is going to be the value of one of these nodes, because every value below that, every value above that we haven't seen yet, and every value below that wouldn't form a good path because it would violate this description we're given. So we're going to have kind of three cases. We're going to say, let's say we have these nodes, we have these connected and these connected, and then we draw this line. What we want is for the root node of each component to be the largest node, the node with the largest value in that component. So for example, here we would say, well, the root node here is node 4 because it has a value of 3. The root node here is node 1 because it has a value of 3. So when we say A comma B equals find A and find B, we're saying find at 0, that's going to return this 1, which has a value of 3. Find at 2, that's going to return this 4 that has a value of 3. So the first thing we want to say is, does this connect any good paths? So the way that we would say that is if vals at A equals vals at B. And then if not, there's two possible options. There's vals at A is greater than vals at B, or vals at B is greater than vals at A. But we don't have to check that, because if it's not equal and it's not greater, it can only be less than. So these ones are pretty simple. We say if the value of A is greater than the value of B, this is sort of A being the marker node of a component that's being connected, then everything in the B component is going to point to A now. So we say root at B equals A, or else root at A equals B. And here is where the sort of complex part comes into it, because we say, okay, we know that we found a good path. Both markers are of the same value. So this is where we want to change answer. And I'm actually going to change this to self.answer so that we can directly modify it from within this this function. And we have to say return self.answer. So if you think about this, let's say you have a connected component where, or you have this line drawn and there's some large connected component over here. And the large connected component has 5 3s. And this large connected component has 2 3s. So how does that change answer once there's a viable connection between all of those? In this very specific example, there's only one good path that isn't just a node to itself. But in an example like that, where you have a bunch of the same value connected to a bunch of the same value, what you're going to wind up with is that's going to be 7 3s now. So that's 7 choose 2 different paths between each of those 2 3s if they're all connected. And there's not any situation where for those 7 3s, 2 of them do have a good path and 2 of them don't have a good path. If that happened, then that would be 2 separate components of 3s. Let's say these values were like 4 and 5. There could be some collection of 3s down here that all have good paths, and some collection of 3s up here that all have good paths. And that's actually why union and find is kind of necessary to keep track of these distinct things, these distinct sets of paths. But if we go back to that example, we've connected all of these 5 to 2. Well, there's a path between one of the 3's in each of the 5 and the other of the 3's in each of the 5. So it's kind of 2 times 5 is the total amount of new connections we've made. And if you think about it, if you have, let's say, a single node of value 3 that gets connected with another node of value 3, that's 1 times 1 new connection. You have 1 connection. And then if those 2 get connected to another node of value 3, well, that's connected to one and the other. So then you have 3 total connections. You've added 2. And then if those 3 get added to another, then you've added 3 new connections. So now you have 6. And if you think about like n choose 2, it follows up with that, because n choose 2 is 1, 2 choose 2 is 1, 3 choose 2 is 3, 4 choose 2 is 6, 5 choose 2 is 10, and so on. So there's a world where you could use the choose 2 algorithm, which is n times n minus 1 over 2. Or you can do it this way, which is more convenient here, to just say every time we connect 2 components, and this is also intuitive, like if there's 5 3's over here and there's 2 3's over here, then it's going to be n times m, where that's the amount of the same valued node in each component, n times m new connections that have been formed. So we would want to say self.ans plus equals size at A times size at B. And now we're kind of using size, and we're using size in a specific way here, where size doesn't just mean the total number of connections of all nodes in a component. Like if, let's go back to this example where we're drawing this connection, this isn't size 3 and size 2. That's a way you could write it if you wanted more of a boilerplate disjoint set algorithm, but the way that we're going to use size is actually to be the number of nodes with the same value in this connected component. So the size here would be 1. The size here would also be 1. And then, but then once we connect them and we're looking at, well, all of these point to node 1 or node 4, and that has a value of 3. That's why they all point, because that's the highest value in this new connected component. That now, let's say node 4, if we chose that over node 1, has a size of 2, because there's 2 3's. And then if we connected to some other component that had a single 3 and a bunch of 1's and 2's, then we would have a size of 3. So we want to say if vals at A equals vals at B, and then we can just say something like we just choose one of these 2. So between 1 and 4, let's say we draw this connection, we just choose 1. So we could say root at B equals A, size at A equals plus equals size at B. And then from there we pretty much just iterate through every edge and run the union. So we say for A comma B in edges, union A and B. And I got pretty caught up in the description there. So, and then the last thing we have to do is say plus n, because we have to include every, or instead of that, we could just say self.ans equals n right here. Because we have to, this doesn't account, this only accounts for choose 2, but we kind of want the choose 1 when it's just one node in itself. So this is blazingly fast. I don't think you can really get faster than this. There's a couple of optimizations we can make, actually. The first one, and this is actually not minuscule, is right here we say root at B equals A, size at A plus equals size at B. In a situation like this, let's say this is the final connection that we draw, and actually it probably would be if right here we say print edges. So we've sorted edges, so node 2 and node 4 is the last node that we draw this connection. So we have this connected component and then this connected component. When we draw this, we say vals at A does equal vals at B, because the root node of this is going to be node 1, and the root node of this is itself, because right now it's an isolated node. So when we draw this connection, we're comparing 4 and 1. And right now, if we say root at B equals A and all this, You know, right here, it would be root at 4 equals 1, but this order is random. This could have easily just been 4 comma 2. And if that was the case, then we would be needlessly reassigning all of these nodes to have this as the root node instead of this one root node to have this as its root node. So we can do, we can gate this behind an if statement and say if size at B is greater than size at A, then say root at A equals B, size at B plus equals size at A, or else in a situation where they're the same or size at A is larger, then do this one. And that does optimize by quite a bit. Or I don't know about quite a bit, but it makes it go from low 90s to consistently above like 95%. So that's the clean and pristine solution, and we even left in the print edges there, and it still was high 90s. It's going in the thumbnail. How long have I been recording? 26 minutes. I think I'll just make a separate video about my hogwash solution. But that's the solution. It uses union find. I would call this sort of definitely heavily leaning on Kruskal's algorithm. And I think the food for thought here is thinking about why you sort edges, and when you're iterating through edges and you're drawing a union and you're performing this action where you're connecting two components in the tree, think about what state the tree is in currently, where when you draw a new node, that could potentially create new paths, new good paths, and how that relates to the maximum between the values of each node in an edge, and how and why you would want to sort this by that. I think that's the really important thing to think about in order to understand this. Hit like and subscribe.